Okay, it has been 9 minutes past 5 o'clock, but no one has joined yet. But I'm going to start discussing the questions anyway because I have to cover up 2 hours. If someone joins, I'm going to repeat the questions then. But this is just for the recording purpose in YouTube. So I'm going to start dictating the questions, discussing the questions, and I'll take a break afterwards and then I'll start discussing the answers like the usual days. Okay, so this is week 4 of soil mechanics geotechnical engineering. I think it is recording. Yes, it is recording. Week 4 of soil mechanics geotechnical engineering, and the topic is effective stress concept and applications. And here, since the topic is effective stress, I'm going to give a brief idea with respect to the questions I dictate. Brief idea on the soil water relationship, the statics of soil and water, and how water is influencing the effective stress, its calculations, and its applications. All right, so I'll start dictating the questions. There are MCQ, true false statements, and there are numericals here. The first question is coarse grained soils have relatively low hygroscopic moisture due to their coarse grained soils have relatively low hygroscopic moisture due to their the options are greater angle of internal friction, limited specific surface, low cohesion, or none of these. Coarse grained soils have relatively low hygroscopic moisture due to their greater angle of internal friction, limited specific surface, low cohesion, or none of these. Next question. Almost reversible swelling and shrinkage on rewetting and redrying can be observed in soil having high content of almost reversible swelling and shrinkage on rewetting and redrying can be observed in soil having high content of. The options are silica, illite, montmorillonite, or kaolinite. Silica, illite, montmorillonite, or kaolinite. The options. Next question. This property offers an explanation for the bulking of sand. The options are slaking, high friction angle, activity, or apparent cohesion. This property offers an explanation for the bulking of sand, slicking, high friction angle, activity, or apparent cohesion. Next question. The maximum capillary tension for a tube of 0.05 mm diameter for water at 4 degrees centigrade is. The maximum capillary tension for a tube of 0.05 mm diameter for water at 4 degrees centigrade is. All the options are in kilonewton per meter cube. The options are 6.05, 7.03, 6.62, 7.05. 6.05, 7.03, 6.62, 7.05 Newton per meter cube. Next question. The pressure transmitted from particles through their point of contact through soil mass is called. The pressure transmitted from particles through their points of contact through soil mass is called. The options are neutral pressure, total pressure, effective pressure, saturated pressure. Repeat the question again. The pressure transmitted from particles through their points of contact through soil mass is called. The options are neutral pressure, total pressure, effective pressure, or saturated pressure. Next question. Entry of air into the void spaces of clays during drying below shrinkage limit, followed by immersion in water causes. Entry of air into the void spaces of clays during drying below shrinkage limit, followed by immersion in water causes. The options are swelling, slaking, shrinking, or expansion. Entry of air into the void spaces of clays during drying below shrinkage limit, followed by immersion in water causes swelling, slaking, shrinking, or expansion. Next question. When the water level in a lake or tank rises, the effective stresses in the soil below increased, decreased, depends on the particle size, remains constant. When the water level in a lake or tank rises, the effective stresses in the soil below is increased, is decreased, or depends on the particle size, or it remains constant. Next question. The effect of capillary saturation will cause the effective stress to. The effect of capillary saturation will cause the effective stress to increase, decrease, can be both, or remain constant. The effect of capillary saturation will cause the effective stress to increase, decrease, can be both, or remain constant. What will be the effect of capillary saturation or capillary suction on the effective stress of the soil beneath? How will it affect the effective stress of the soil? Will it increase or will it decrease? Or it can be both depending upon other conditions which are not mentioned over here, or the effective stress will remain constant no matter how much the capillary suction increases or decreases. Effective stress might increase or decrease, might do both, or it might remain constant. All right. Next question. This is a true false statement. Structural water can be removed by oven drying at 55 to 65 degrees centigrade. Structural water can be removed by oven drying at 55 to 65 degrees centigrade. Tell me if this statement is true or false. Structural water can be removed by oven drying at 55 to 65 degrees centigrade. Is this statement true or false? Next question. In the capillary saturated zone, the pore pressure is. In the capillary saturated zone, the pore pressure is tensile, compressive, Can be both, or it is 0. In the capillary saturated zone, the pore pressure is tensile, compressive, can be both, or 0. That is a region of the soil where capillary suction occurs. That portion, that layer of the soil where the capillary suction occurs, what will be the nature of pore pressure or neutral pressure? What will be its nature? Whether it will be tensile or it can be maybe compressive. It can be tensile or compressive depending upon other factors which are not mentioned over here. In that case, the other factors need to be mentioned, or it will be 0. Next question. This is a numerical. Water table was found 1 meter below the ground surface. Above the water table, the soil was saturated with capillary water. If the saturated unit weight is 18 kilonewton per meter cube, the effective stress at the water table level in kilonewton per meter cube is. It will be kilonewton per meter square. The unit weight is the stress. It will be in kilonewton per meter square. Pardon. So the water table was found 1 meter below the ground surface. Now above the water table, the soil was saturated with capillary water. It means capillary suction was taking place in the soil above the water table. Now if the saturated unit weight of the soil is 18 kilonewton per meter cube, the effective stress at the water table level in kilonewton per meter square is. The options are 8, 9, 18, or 0. 8, 9, 18, or 0. I'll repeat the question once. Water table was found 1 meter below the ground surface. Above the water table, the soil was saturated with capillary water. If the saturated unit weight is 18 kilonewton per meter cube, the effective stress at the water table level in kilonewton per meter square is. The options are 8, 9, 18, or 0. Okay. Next question. Then another true false statement. Hygroscopic moisture can change due to gravity or capillary action only. Hygroscopic moisture can change due to gravity or capillary action only. Is this statement true or false? Hygroscopic moisture can change due to gravity or capillary action only. Is this statement true or false? Next question. Neutral pressure means pore pressure, the pressure exerted by the water. So neutral pressure is always tensile, always compressive, compressive below water table and tensile above it, compressive above water table and tensile below it. This question is demanding the basic nature of neutral pressure or pore pressure. How does neutral pressure or pore pressure behave in general? Neutral pressure is always tensile, always compressive, compressive below water table and tensile above it, compressive above water table and tensile below it. Next question. The effective stress in kilonewton per meter square at a depth of 10 meter below the ground level when water table is 3 meter below the ground level, saturated density is 20 kilonewton per meter cube, that is saturated unit weight, and bulk density or bulk unit weight is 18 kilonewton per meter cube. You have to find out the effective stress in kilonewton per meter square at 10 meter below the ground level. The options are 154, 124, 194 or 144. So there is a soil layer and water table is 3 meter below the ground level. To find out the effective stress at 10 meter below the ground level. The saturated density is 20 and bulk density is 18. Here, since gamma W is not given, you can consider gamma W as 10 kilonewton per meter cube. The effective stress in kilonewton per meter square at a depth of 10 meter below the ground level when water table is 3 meter below the ground level, density is 20 kilonewton per meter cube and bulk density is 18 kilonewton per meter cube. Is the options are 154, 124, 194 and 144. Okay, next question. In the capillary fringe, the effective stress is less than total stress, greater than total stress, equal to total stress, or it can't be said. In the capillary fringe, the effective stress is less than the total stress, greater than the total stress, equal to total stress, or it can't be said. That means it can't be said. It depends upon other parameters which are not mentioned over here. So the relationship between total stress and effective stress is being asked to be mentioned in this question, and that is with respect to the capillary fringe. That is the portion where capillary suction is taking place. So what will the effective stress be? It will be less than total stress, or more than total stress, or equal to total stress, or it can't be said. Next question. Softening of soil due to melting of ice is commonly known as softening of soil due to melting of ice is commonly known as the options are frost heave, bulking, slaking, or frost boil. I'll repeat the question. Softening of soil due to melting of ice is commonly known as softening of soil due to melting of ice is commonly known as the options are frost heave, bulking, slaking, or frost boil. This melting of ice and softening is being considered with respect to the zone where capillary suction has taken place. Capillary suction has taken place previously, and then the water has melted, after which the phenomenon which goes on, water has frozen first and then it has melted. Then the phenomenon which goes on is called frost heave or bulking or snaking or frost boil, due to which the soil softens. Okay, next question. Another numerical, a river 5-meter deep consists of a sand bed with saturated unit weight of 20 kilonewton per meter cube. Here gamma W is given as 9.1 kilonewton per meter cube. The effective vertical stress in kilonewton per meter square at 5 meter from the top of sand bed is. A river 5-meter deep consists of a sandbed with saturated unit weight of 20 kilonewton per meter cube and gamma W is 9.1 kN per meter cube. What will be effective vertical stress in kilonewton per meter square at 5 meter from the top of sandbed? The question is pretty straightforward. The options are 41, 60, 50 or 51. Next question is, the depth of water in a swimming pool is 6 meter. The total and effective stress in kilonewton per meter square at depth of 3 meter below the top surface of water is. Here, the depth of water in a swimming pool is given, and we are asked to find out the total stress and effective stress at a depth of 3 meter below the top surface of water. Here gamma W is not given, that means you have to consider gamma W as 10 kilonewton per meter cube, the unit weight of water. The options are total and effective stress. The first one is coming in the first option, the second one in the second option. That is 10, 30, 10 is the total stress and 30 is the effective stress. 10, 30, 20, 20, 0, 30 or 30, 0. The depth of water in a swimming pool is 6 meter. The total and effective stresses in kilonewton per meter square at a depth of 3 meter below the top surface of water is. The options are 10, 30, 20, 20, 0, 30 or 30, 0. Next question. A 2-meter thick sand layer of density 1.7 ton per meter cube overlies a 4-meter thick saturated clay of density 2 ton per meter cube. If the water table is at the interface, that is, at the interface of the two layers, sand and clay, the effective pressure in ton per meter square at the center of the clay layer is. So first there is a sand layer. The thickness is 2 meter and the density, or the unit weight, density over here is being considered ton given in ton per meter cube. So it is 1.7 ton per meter cube. It overlies, it lies above a 4-meter thick saturated clay of density 2 ton per meter cube. Now the water table is situated at the interface, that is at the interface of the sand and the clay layer. In this case, the effective pressure in ton per meter square at the center of the clay layer is. The options are 7.4, 5.4, 2 or 3.4. A 2-meter thick sand layer of density 1.7 ton per meter cube overlies a 4-meter thick saturated clay of density 2 ton per meter cube. If the water table is at the interface, the effective pressure in ton per meter square at the center of the clay layer is 7.4, 5.4, 2 or 3.4. Next question. The ground conditions in a site are shown below. We have a sand layer of 5 meter thick. Up till the point P, we have the water table at the top of the sand layer. At the ground level, moisture content is 20%, specific gravity of soil surface is 2.7, unit weight of water is 10 kilonewton per meter cube. Now in these conditions, we have to find out the saturated unit weight of sand using a formula, and then to find out using that the total stress, pore water pressure and the effective stress at the point P. Water table is at the ground level. Moisture content is 20%, specific gravity of solids is 2.7 and unit weight of water is 10 kilonewton per meter cube. Find out the saturated unit weight of sand in kilonewton per meter cube, and in the same unit you have to find out the total stress, pore water pressure, and the effective stress at the point P, 5 meter below the ground level. Next question, quicksand condition occurs when? Quicksand condition occurs when? The options are effective pressure becomes less than 1, effective pressure reduces to 0, effective pressure is equal to atmospheric pressure, or none of these. I repeat the question, quicksand conditions occurs when effective pressure becomes less than 1, effective pressure reduces to 0, effective pressure is equal to atmospheric pressure, or none of these. Next question. The sand stratum, as you can see, is overlain by a saturated clay having unit weight of 18.5 kilonewton per meter cube. At 8-meter excavation depth, water started entering the trench from below. After excavating for 8 meters, the water started entering the trench. Now unit weight of water is taken as 10 kilonewton per meter cube. To calculate the height in meters to which water would have risen from the top of sand in the borehole shown as HW if the borehole was drilled prior to the excavation. Now at first the borehole should be drilled over here, after which the excavation will be started, and at 8 meter water started entering this trench. So what will be the height in meters of the water in this borehole if this borehole was drilled prior to the excavation? The total width is 12 meter, but here it is shown as 8 meter and 4.5 meter, so we will not consider 12 over here, we will consider 12.5 over here. And Z is the main important thing over here because it is the still overlain top portion of the clay layer. Z is important, is 4.5. Okay, so this is important. So considering this, the options are 8.839, 7.328, 8.325, 7.632, all are in meters, the height of water in this borehole. Z and 8 meter is important. You can ignore this 12 meter height. The data given is unit weight of the soil is 18.5 kilonewton per meter cube of this saturated clay layer, and unit weight of water is 10 kilonewton per meter cube. Next question. Water is flowing at a rate of 0.04 milliliter per second in an upward direction through a fine sand sample whose coefficient of permeability is 2 into 10 to the power of minus 3 centimeter per second. The sample thickness is 10 centimeter, cross-sectional area is 45 centimeter square, and its saturated unit weight is 1.93 gram per cc. Determine the head causing the flow in centimeter and the effective stress at the bottom of the soil in gram per centimeter square. I repeat the question. Water is flowing at a rate of 0.04 ml per second in an upward direction through a fine sand sample whose coefficient of permeability is 2 into 10 to the power minus 3 centimeter per second, that is K. The sample thickness is 10 centimeter, cross-sectional area is 45 cm square, and saturated unit weight is 1.93 gram per cc. Now under this condition, to find out the head causing the flow in centimeter and the effective stress at the bottom of the soil in gram per centimeter square. So I have finished editing the questions. I'll take a break right now because still no students have joined this session as of now. Yes, no students have joined this session as of now. So I'm going to take a break and I'm going to start discussing the answers after a few minutes. After around 10 minutes, I'll start discussing the answers. Okay, I'll be starting to discuss the answers, the solutions of the questions right now. I'll be waiting for a few minutes, a couple of minutes. Anyone joins this time. Start at 6:03 because no one has joined yet. So wait for a couple of minutes. Okay, so the first question of this live session was coarse grained soils have relatively low hygroscopic moisture due to their, in the case of coarse grained soils, they have a limited specific surface, that is surface area per unit mass is low, is less than the fine grained soils, clay and silt. Because of this, their absorbing capacity of water on the surface is low, and due to this, they have low hygroscopic moisture. I'll repeat, coarse grained soils, they have a low value of specific surface, that is surface area per unit mass. Because of this, they have less capacity of absorbing moisture on their surface, due to which they have comparatively low hygroscopic moisture as compared to the fine grained soil. So in this case, the answer will be limited specific surface. Okay. Next question. Almost reversible swelling and shrinkage on re-wetting and re-drying can be observed in soil high content of having a high content of which mineral? Silica, halite, montmorillonite, and kaolinite. Montmorillonite is a component present in black soils which exhibit high swelling behavior. the case of montmorillonite, in the case of black soils, it exhibits swelling behavior due to montmorillonite, and because of this montmorillonite, reversible swelling and shrinkage occurs on re-wetting and re-drying. Volume change, large amount of volume change can be observed in soil having high quantity of montmorillonite. So the answer here is option number 3, montmorillonite. Almost reversible swelling and shrinkage on re-wetting and re-drying can be observed in soil having high content of montmorillonite. Next question. This property offers an explanation for the bulking of sand. Now, in case of in the case of bulking of sand, plot the volume percentage volume increment with the moisture content. Then we can see that for coarse grained soil the graph will go like this, but for fine grained soil the graph will go like this. Not coarse grained soil, for coarse grained sand and fine grained sand, bulking occurs in only sand. So fine grained sand or fine grained and sand, this is coarse grained. Now in this case there is an interparticle adhesion due to the capillary action of water, because of which on addition of moisture the volume increment occurs up till a certain level. Has anyone joined? Because of which uh, the action of water leads to an increment in volume. This property is also called apparent cohesion. It seems like there is cohesion among the particles, but actually there is no cohesion. It is the interparticle adhesive force in action due to the capillary action of water. Because sand is a coarse grained soil, uh, it will not have any cohesive force. But due to interparticle adhesion under the action of capillary water, the volume increment occurs, which leads to the phenomenon called bulking of sand. I hope it is clear. The next question is the maximum capillary tension for a tube of 0.05 mm diameter for water at 4 degrees centigrade is. Now there is a formula for the maximum height of capillary is HC max is equal to 0.3084 whole divided by D. In D should be in centimeter. Now if you put the value of D in centimeter, this is 0.5 centimeter, you get HC max, that is the maximum height of capillary water in the tube will be equal to approximately 0.617 meter. 0.617 meter. Now if you want to find out the capillary tension in the tube, then how can we get it? Get it by capillary tension equal to HC max into gamma W. Gamma W is 9.81. HC max into gamma Kn per meter cube. Gamma W equals to 9.81 Kn per meter. Here we are taking gamma W as 9.81 and not 10 because the value of gamma W is very crucial to get the appropriate answer, the right answer. So we cannot let any mistake happen because of the decimal places. Multiplying this, we'll get 6.05. The answer is 6.05 kilonewton per meter cube. So HC max equal to 0.3084 by D in centimeter will give us the maximum height of capillary action in meters. That multiplied by gamma W will give us the capillary tension for the tube of that particular diameter. I hope it was clear. Go to the next question. The pressure transmitted from particles through their points of contact through soil mass is called. It's a very easy question. Grain to grain transfer of pressure is called effective pressure. The pressure transmitted from particles through their points of contact, neglecting the water pressure, only the particles which are existing in the soil, the pressure transmitted through those particles to their point of contact is known as the effective pressure. Effective pressure plus neutral pressure will give us the total pressure. Okay, next question. Entry of air into the void spaces of clays during drying below shrinkage limit followed by immersion in water causes. Now, what is shrinkage limit? We have seen in the consistency limits. These are the consistency limits. This is the liquid limit. This is the plastic limit. This is the shrinkage limit. This is the volume. This is the moisture content. Now after shrinkage limit, there is no decrement in volume from the right to the left. So when water is being removed from the clay and air enters into the void spaces during drying. Now after air enters the void spaces, if the sample is then immersed in water, then what happens? A high pressure arises in the soil which leads to the disintegration of the soil structure. Because of the increment in pressure, it increases after immersion because of the entry of water suddenly in the air voids, and there is a disintegration of the soil structure, breaking down of the soil structure. This phenomenon is called slaking of clay. So on drying below shrinkage limit, after the soil sample is immersed in water, high pressure arises in the soil due to the entry of water, after which disintegration of the structure happens, and this is called slaking of the clay. It happens only in clays. I hope it was clear. I go to the next question. When the water level in the lake or tank rises, the effective stresses in the soil below. So when the water level in the lake or tank rises, effective stress means grain to grain transfer of stress of the soil to their point of contact. So the grain to grain transfer of stress, it does not have any effect, or the change in the water level does not have any effect on the grain to grain transfer of soil stress, and hence I can say that the effective stress in the soil below, when the water level in the lake rises, the effective stress in the soil below, it remains constant. Sorry for the interruption. There was a problem with the video. So the effective stress, it remains constant even if there is a rise or even if there is a fall in the water level in a lake or a tank. Okay, go to the next question. The effect of capillary saturation will cause the effective stress to. What will happen to the effective stress if the capillary suction happens? Capillary suction happens. Now, the effective stress in capillary suction in the zone of capillary saturation will increase because since the pore pressure, that is U, will be acting in the upward direction, and we know total stress equals to effective stress plus U. So effective stress equals to total stress minus U. Here U is negative, so effective stress will be total stress plus U. Effective stress will increase. Effective stress will increase because due to the capillary suction of water, the grain to grain transfer of soil will increase because the total stress will remain constant. So effective stress will be more than total stress, and effective stress will increase under the effect of capillary saturation. Next question. Structural water can be removed by oven drying. It is false because structural water is bound by chemical compositional elements in the soil, so it cannot be removed by oven drying. That too at a very low temperature, 55 to 65 degrees centigrade. Beyond 110 degrees centigrade, it can be removed, but not in this low range of temperature. Next question. In the capillary saturated zone, the pore pressure is. So I have said earlier, this is the water table. This is the soil above the water table. This zone is capillary saturated, and in this zone it is saturated. So this is the line. This is the line. Then this part, the pressure will be positive or compressive, and in this part, the pressure will be negative or tensile. So in the capillary saturated zone, the pore pressure is tensile, is negative, that's upwards. Okay, hope it was clear. The next question is, water table was found 1 meter below the ground surface. Above the water table, the soil was saturated with capillary water. If the saturated unit weight is 18 kilonewton per meter cube, the effective stress at the water table in kilonewton per meter square is. Someone has joined? Yes, okay. One person has joined. Please write down the question from this part. I have already mentioned the previous questions. You can check the video which will be uploaded in the YouTube today for the previous questions. Okay. Okay. So the question is, water table was found 1 meter below the ground surface. Above the water table, soil was saturated with capillary water. Now, this is the ground surface. This is 1 meter below the ground surface. This is the water table saturated with capillary water over here. Now, saturated unit weight is 18. Gamma sat is 18. Okay, so effective stress at the water table level. So as I've said, effective stress in this zone will be more than the total stress. So in the case of effective stress, we are going to consider the entire soil saturated with water. That means effective stress will be over here, not gamma submerged, but gamma sat equal to gamma sat equal to gamma sat into depth. Depth is 1 meter. That will be equal to 18 kilonewton per meter square. So effective stress will be gamma sat into 1, that is 18 into 1, 18. Now total stress, if it was asked, that would have been equal to gamma sat into 1 minus gamma w into 1. That is, gamma w would have been acted in a negative way to decrease the total pressure, because in this case effective stress will be more than the total stress. I hope the concept was clear. I'll go to the next question. Is it clear? This. Okay. Next question. The true false statement. Hygroscopic moisture can change due to gravity or capillary action only. Hygroscopic moisture is a moisture that is being adsorbed on the surface of the soil and cannot change due to gravity or capillary action. So this is false. Okay. Next question. Neutral pressure is, what is neutral pressure? I hope you know what neutral pressure is. Neutral pressure is nothing but the pore pressure. Neutral pressure is, I have already said it, the same question in a different way. The water table, this is a line. So below water table it is positive. Above water table, if it is there, then it is there by capillary action, so it will be negative. That is tensile above the water table and compressive below the water table. This is tensile zone, this is the compressive zone. Compressive below water table and tensile above it. Clear? Still there? Next question. The effective stress at a depth of 10 meter below the ground level when water table is 3 meter below the ground level, saturated density is 20, bulk density is 18. So now this is the ground level. Hello, the PPT is visible, right? Suchi, you've joined late. Okay, write down the solutions from this question. Someone else also joined, but not there. So this is the ground level. Water table is 3 meter below the ground level, and to find out the pressure, the depth of 10 meter. That is, this is 7 meter. This is 3 meter. So bulk density is 18. saturated density is 20. Nothing is given over here, so we'll consider gamma W equals to 10 kilonewton per meter cube. So at this depth, what will be the effective pressure? The effective pressure will be first 18 into 3. I have already started the class and I have already discussed the answers. You have joined late, so please follow the questions and the solutions from now on until the end of the discussion. You can find the entire lecture which has been recorded now in the YouTube channel. Okay. Suchi and Ravi. Yes. Okay. Yes. So in this dry part, it is 18 to 3. Is 18 into 3 gamma W into H. And for the part below water table, we'll take gamma submerged, that is 20 minus 10, 20 minus 10, 20 minus 10 into H, that is 7. So 18 to 54, 54 plus 70 gives us 124. That is in kilonewton per meter square, it is 124. This is the effective stress at this level, XX dash. Okay, 10 meter below the ground level. Now, if we are told to find out the total stress, then we would have considered 20 into 7. 20 into 7 gives us 140 plus 54 will give us 194. That means another 70 will be added to 124, that is 194 is the total stress over here. But I have asked the effective stress, so the answer is 124. I hope it is clear. Okay, if you stay in the meeting, then what I'll do, I'll just do a quick recap of everything, every answers up till slide number 14. Okay, I'll go to the next question. I'll go to the next question. In the capillary fringe, the effective stress is, I have already said this, effective stress is more than total stress, because in the capillary fringe, effective stress becomes sigma total stress plus U, because U is negative in the capillary fringe, U is tensile. So effective stress is more than total stress. Effective stress is greater than the total stress in the capillary fringe. Because of capillary action, U is tensile or U is negative. So the general formula is sigma equals to sigma dash plus U. Since U is negative, sigma dash becomes sigma plus U. This equation changes to this. This is the equation in the capillary fringe. The next question is, softening of soil due to melting of ice is commonly known as melting of ice in the capillary fringe. What happens is, in the capillary fringe, first ice, if the water is frozen, form ice, and then the melting starts. Okay, the soil, it starts softening. This process is called frost boil. Frost heave is the opposite, the freezing of water to ice, and this condition is called softening of soil to melting of ice in the capillary region is called frost boil. Ice formed in the capillary zone when it starts melting. It's clear? Mohammed Hanif.
Yes, yes. Okay.
Okay, next question. A river 5 meter deep consists of a sand bed with saturated unit weight of 20 kilonewton per meter cube, gamma W equal to 9.81. The effective vertical stress in kilonewton per meter squared 5 meter from the top of the sand bed. Now, so this is the top of the river, and this is the sand bed. The sand bed, from the top of the sand bed, the vertical stress at 5 meter. Okay, gamma W is given 9.81. The effective vertical stress. So in this case, the effective vertical stress, the water, this is 5 meter, and this is also 5 meter, and this is the sand. The water above will not play any role in the effective vertical stress. Why? Because effective stress means the grain to grain transfer of water, the grain to grain transfer of grain to transfer of pressure or stress. The grain to grain transfer of pressure is called effective stress, and the water on top of the sand layer will not have any influence on that. So in this case, we are going to consider only the submerged unit weight of the sand. The saturated unit weight is 20. The submerged unit weight will be how much? 20 minus 9.81, and that multiplied with 5 will give us the answer. So the effective stress at xx, that is 5 meter below the sand layer, will be gamma saturated minus gamma w 9.81 into z, that is how much? 5. Doing this, we'll get a value of 50.95. Rounding it off, we'll get a value of 51. So 51 is the effective stress. In this question, we are disregarding the water of the river above the sand because we are asked to find out the effective vertical stress. If it was the total vertical stress, then the water would have been considered and the saturated weight of the sand would have been considered. I hope it was clear. Next question. The depth of water in a swimming pool is 6 meter. The total and effective stress, the depth of 3 meter. So whatever the depth may be, we are asked to calculate the depth pressure at a depth of 3 meter. This is water, only water. Okay. If it's only water, then effective stress will be 0 because there is no soil and there is no grain to grain transfer of load. So effective stress is 0. And total stress is the stress of pressure of water. So nothing is given over here. We consider gamma W equals to 10. So 10 into 3 becomes 30. So total stress equals to how much? Gamma W, that is equals to 10 that is equals to 10 into 3 is the height of the water level. This gives us 30 and effective stress is 0. So the answer is 30 and 0. Is it clear? Is there any doubt?
Clear.
Next question. A 2-meter thick sand layer of density 1.7 ton per meter cube overlies a 4-meter thick saturated clay of density 2 ton per meter cube. So here we have two soil layers. And we are asked to find out at the middle. Now this is sand and this is clay, saturated clay. So if the entire thing is 4 meter, this will be 2 meter, this will be 2 meter, and the sand layer has thickness of 2 meter. Now water table is at the interface, is at here. Okay, so for sand we'll consider the bulk unit weight, that is bulk density, or 1.7. And for clay, to find out the effective pressure, we'll consider the submerged density, right? Now for water in ton per meter cube, the gamma W value is equals to 1 ton per meter cube. So now the value of effective stress will be equals to, at this level, x dash will be equals to, firstly the stress due to the pressure due to the sand layer, that is 1.7 into 2, then the clay layer up till the mid layer, that is plus what we'll consider, the clay has a density of 2, so 2 minus gamma W is 1, is the gamma submerged value we get, into how much, into 2. So here we get, in the first part of the equation we get 3.4, and second part we get 2. 3.4 plus 2, we get 5.4 ton per meter square. So the sand layer, we will be considering the bulk density of sand, because there is no water table present, and the sand is dry. And for clay, we will be considering the submerged unit weight, because the clay layer is saturated, and here we are asked to find out the effective pressure only. If it was total pressure, then it would have been 2 into 2, that is 4, plus 3.4, that is 7.4, the first option, because at that time we will be considering the saturated unit weight of the clay layer. Okay, I hope it is clear. Okay, next question. All right, so here we to find out first the saturated unit weight of sand in kilonewton per meter cube. I've already explained the question. There is a groundwater level, there is a water table at the ground level. Sand has a water content of 20 percentage, specific gravity is 2.7, and unit weight is 10 kilonewton per meter cube of water. Now at a point P, we to find out the stress. The first saturated unit weight of sand, that is the gamma sat. What is the formula? G plus S E gamma W divided by 1 plus E. G plus SE gamma W divided by 1 plus E. How to find out the value of E? E equal to WG divided by S. Now it is saturated, S equals to 1, W equals to 0.2, G equals to 2.7, we get the value of E as equal to 0.54. 2.7 into 0.2, 0.54. Put in the value of E 0.54 and S equals to 1, gamma W equals to 10 kN per meter cube, G as 2.7. We get gamma sat, that is the answer of the first question, as 21.04 kilonewton per meter cube. 21.04 given in the same unit. Okay. Now the second part, total stress. Total stress will be sigma equal to gamma sat into what? The depth 5. That will be equals to 21.04 into 5, that is 105.2. in kilonewton per meter cube. What is the pore pressure? That is U. U is gamma W into 5. That is the 10 into 5 equals to 50. Kilonewton per meter cube. And hence effective stress will be equals to how much? Sigma minus U, that is sigma minus U, we get the value as 50. The value as 55.2 kilonewton per meter cube. Okay, I hope it is clear. Gamma sat into Z, gamma W into Z, and then sigma minus U. Okay. Next question. Quicksand condition occurs when? So obvious question, very simple question. Effective pressure, it reduces to 0. At that time, the quicksand condition occurs. The seepage pressure becomes equal to the total pressure and effective pressure reduces to 0. Now the next question is to find out the height of the water in the borehole. So as I mentioned, the borehole was drilled prior to the excavation. This borehole was drilled prior to the excavation. So when water starts seeping out, or water start what to say, entering this trench in this layer, that means we can say that quicksand condition, not quicksand condition, the effective pressure has reduced to 0 in the first case. That means the grain to grain transfer of load by the soil pressure is not enough to hold the water. In that case, what will happen? The effective pressure will be equal to 0. Effective pressure, that is sigma dash, will be equal to 0. And what is sigma dash? Sigma dash will be total pressure, that is gamma sat into Z minus gamma W. Now here is the interesting thing. Gamma W will not be multiplied with Z, because since the borehole was drilled prior to the excavation, the height of water will be different from the value of Z. That is what we are going to find out over here. The water pressure was initially higher than this value of Z. Hence, the water started seeping out. We'll keep it as HW because we know the value of gamma W. Now we will solve this. Now this is equal to 0. So HW will be equal to Z gamma sat divided by gamma W. So Z is 4.5, gamma sat is being given over here 18.5, and gamma W we are asked to consider as 10. Consider as 10. So now putting all the values, you get a value is option number 3, 8.325. So here we have to remember that as the water starts entering the trench below, the water pressure was initially, the level of water was initially higher than the depth of the trench. And to find out that, we have to equate the effective pressure equal to 0. And effective pressure means gamma sat into Z minus gamma W into the height of water in the borehole. Okay, because the water pressure is being calculated on the interface of the sand layer and the clay layer, and the borehole is drilled into the sand layer. So whatever the pressure of water is in the sand layer, that is being exerted on the clay layer, because of which the water starts entering the trench from below. So in this sand layer which is permeable, here the water was initiated at a certain height, because of which there was a head of water, and that head of water was playing a role while the water was entering the trench from below. Is it clear? Okay, next question. 3 to 5 years. Yes. So in this question, we have the flow rate, we have the value of K, we have sample thickness, we have the cross sectional area, and we have the saturated unit weight. So what we can do, first of all, we can find first of all the submerged unit weight. Gamma submerged equal to gamma sat minus gamma W. Gamma sat is 1.93, gamma W is 1 gram per cc. We get 0.93 gram per cc. To find out the head causing flow in the first case, what is Darcy's law equation? That is Q equals to K I A, and K I A, that is I means what? I is the head causing the flow divided by the length of traverse into A. Now you can see that head causing the flow will be equals to how much? Will be equals to Q into the length of traverse divided by K into A. Putting all the value over here, it is Q equal to 0.04 milliliter per second. Okay, milliliter means cc. L is equals to 10 centimeter sample thickness, cross section area is 45 centimeter square, and K is 2 into 10 to the power minus 3 centimeter per second. You get a value of H, that is equals to 4.44 centimeter. Four point 44 centimeter. Okay, now we have to find out the effective stress at the bottom of the soil in gram per cc. So if this is the layer of the soil and the water is rising up like this in upward direction, then what will happen? This is L. Okay, so effective stress will be calculated not with respect to gamma sat but with respect to gamma submerged. So we can say that L into gamma submerged, that is the downward force, minus the upward force, that is the head causing the flow, into gamma W, will be the effective stress at the bottom of the soil in gram per centimeter square. Now the value of L we know, that is the value of L is 10 centimeter. The value of L is 10 centimeter. Gamma submerged is 0.93. So it is 9.3 the value of the downward force, minus the head causing the flow into gamma W, is 1 gram per cc, minus 4.44, we get a value of the effective stress as 4.86 gram per 6 gram per centimeter square. Okay, 4.86 gram per centimeter square. So this part is the downward force, this part is the upward force. Okay, downward force minus upward force gives us the effective stress in gram per centimeter square, or downward stress minus upward stress. Is it clear? Any doubt? Anyone? Yes, there is one. Yes. Okay, if there is no doubt, I believe I can end the session. Okay, welcome.